Okay, so in the previous video, we learned what can be a parameter and what cannot be a parameter. So simply speaking, a parameter should be non-random, should be fixed, and unknown, of course. So now that's simple, it is easy to set the target. But the problem is how to hit the target. That is a main problem. So in other words, how to construct or how to calculate an estimator for the parameter of interest once you set the parameter. Okay, for example, in this chapter, I will only consider estimating the expectation of x, right? So, and also this is simple, like maybe the simplest estimation. Also, it is pretty useful and widely applicable. As you know, a lot of things can be represented as expectation. For example, variance is another kind of expectation, right? And in binary distribution, the probability can be interpreted as a mean, right? So understanding the estimator of a mean is like more useful than you may think, right? So anyhow, suppose that our parameter of interest is the mean of a random variable x. In that case, okay, how can we calculate the estimator? How do we estimate this? So maybe you may think just you can use simple mean. That is right, but you have to think about some alternatives. For example, you may think simple mean after deleting the minimum and the maximum, right? So in some sports, we use this kind of grading system, dropping the minimum and the maximum and calculate the average within the middle ones. Or how about using a median, right? Median and mean are, measures of the central location. So a median could make some sense, right? So in this video, we are going to think about two problems. First, what can be and what cannot be an estimator. Something cannot be an estimator. Second, okay, so then once you know like what can be an estimator, then that means there are candidates. There are different candidates of estimators. And then what is the best, or how can we tell one estimator is better than another? Like so, as I said, first we are going to think about the requirement for an estimator, and second, we would like to think about the desirable properties of an estimator, or good estimator. Okay, so that's our main theme here. So first, for something to be an estimator, it should be a statistic used to estimate a parameter. So that is the definition, right? Estimator is something to estimate a parameter. So, like in our example of gas price, so you'd like to estimate the mean of the gas price in New York City using 100 gas stations, right? Suppose that there are infinite number of gas stations in New York City, but you only observe 100. And so now you're estimating the mean. But like, I'm not saying what is a good estimator, but so one of these five cannot be used as an estimator. Like say, any number came to your mind, such as like 10. Just choose any number you have in mind, like 100. Doesn't matter, on billion. Any number. B, half of the sample average. For some reason, you divide the average by 2, like x bar over 2. And C, sample variance. We are estimating the mean, but how about using variance? D, population mean of the gas price, as if you observe everything. E, and the gas price at the nearest gas station. Okay, there are 100 observations, but I don't care. I will use the gas station in front of me. What cannot be an estimator? Of course, most of them are absurd estimators, but I don't care if it's good or not. Well, I'm asking you about the basic minimum requirement for an estimator. Think about it. So, at minimum, an estimator for an estimator, you should be able to calculate that, right? If you cannot calculate that, then that is not an estimator. Among these 5, D is not available. So think about this. Population mean is actually what you want to estimate. You don't know this, so you'd like to estimate this. So it cannot be an estimator, right? So all the other options, choices are absurd. Like, why do you use variance for mean? I understand it is wrong, like it'll be kind of weird, but at least you can calculate that. That is minimum requirement. You should know a number. You should have a number to say something, to answer the question, right? So now it is simple. The first requirement was simple. Requirement is simple, like you should be able to calculate the estimator. That is minimum requirement. And then the next question is, what is a good estimator? Okay, I showed you I showed you some absurd estimators. Then in what sense they are wrong or they are absurd, right? That's we are going to develop 2 criteria to tell why it is not a good estimator, right? That's our next and main theory we are going to learn in this chapter. So to understand that, it needs some background. First, you should understand that an estimator is calculated from a sample, and remember, sample is random because it's randomly sampled, literally. So if you choose another set of random sample, then the estimator may be different. So estimator is calculated from a sample, like sample average, sample variance, sample probability. But if you repeat the experiment of random sampling, you may have a different value. So in that sense, the estimator is also random, right? So I'm doing this, repeating this in from the previous chapter. So then we are going to, our criteria for a good estimator should depend on the sampling distribution of this estimator, right? For example, we learned a sample average will be approximately normal distribution with specific mean and variance. So that will be our criteria for determining what is a good estimator. And one extreme is like this. A perfect estimator would be like this. So theta hat is your estimator. Theta is the true parameter. So if they are equal, you are correct. Your estimation is perfect. And I hope this to happen with 100%. So sometimes, because theta hat is random, sometimes theta hat may be equal to the true parameter, or sometimes not. But what we want is they are equal 100%. This would be the perfect estimator, right? So, but of course it is impossible. If you have something like this, you don't need statistics again, right? You are just certainly you know the answer. It means you know the answer. So in reality, what we have is like this. So say true parameter was here. We don't know in practice, but theoretically you can imagine assume that there is a true parameter here. And then if true parameter was here, what would be the probability distribution, sampling distribution of the estimator? It would be like a normal distribution according to the central limit theorem in many cases. In many cases, the estimator will be like this. So that means your estimator may fall here or may fall here. And that is this when the density is high, you are more likely to get that number. But as you go to the tail, the probability will be lower, so you are less likely to get that value as an estimator. Okay, so this is the distribution of your estimator. So let's think about this sampling distribution. So if you happen to get this number, if you happen to have this realization, your estimator is realized at this point. That is possible. And then you may think this is your estimation error. Your estimator is here, the true parameter is here. So the difference is your estimation error, which is obvious, okay? So then, of course, what we want is the estimation error to be small, to be 0 to be exact, right? And then, also, what we care about is the sign. Like, if your estimator falls on this side, on the right side of the true parameter, you are overestimating. Say, for example, true parameter is, say, 100. But your estimator could be, say, 200. That is overestimation. So this area represents the probability of overestimation, right? If your estimator falls onto this interval, overestimating the true parameter. Similarly, the other side is underestimation, right? So your estimator falls below the true parameter. So the area is underestimation probability. So, or you may, from the sampling distribution, what's also interesting is the probability within a certain margin. Say true parameter is here. Say suppose that you are interested in the probability that your estimator is plus minus 10 within the error is up to 10, plus 10 or minus 10. Then you can think about an interval which contains all the points within plus minus 10 from the true parameter, and you can calculate the probability as the area on that interval. This is another interesting way to measure how good your probability, your estimator is, right? Okay, so this is how we understand the sampling distribution, right? When you have a sampling distribution, you can think about probability of estimation error, and a lot of things: overestimation, underestimation, and margin from the true parameter. And then what actually we are doing is we are comparing two distributions, right? So when you have, say, you are comparing two parameters, you'd like to decide which estimator is better. In that case, what you have to do is, for each estimator, you have to think of its sampling distribution. So if you have two estimators, they may have different sampling distributions, and we are comparing those sampling distributions. That is the main point. For example, suppose that you have blue estimator and orange estimator. So blue and orange have different distributions relative to the true parameter, right? So in this case, as you can see, orange estimator has a wrong center. Blue estimator is correctly centered at the true parameter, but orange is not. How can we interpret this? Simply speaking, orange estimator tends to be greater, on average, greater than the true parameter. So it tends to overestimate the true parameter. So that is not desirable. So when you compare the blue and orange in like this, then what you can say here is, I would say blue estimator is better because it does not have any tendency for overestimation or underestimation. It is correctly centered. On average, it is correct. Even though there can be errors, but on average, the error is expected to be 0. But orange is not. Orange is expected to overestimate the true parameter. So blue is better in this case. That is one example. Another example, in this case now, you have blue estimator and green estimator. How can you compare them? So now the difference, they are correctly centered at the true parameter. Both are correct in terms of their center, right? So none of them has a overestimation or underestimation problem. but their difference is spread, the variability. So green estimator is more variable than the blue one. In other words, green estimator has more probability to have larger estimation errors. Okay, so the tail probabilities are higher. That means the tails are kind of larger estimation errors. So in this case, blue is also better. So blue estimator has higher probability close to the true parameter compared to the green one. Okay, so the variability is related to the reliability, how reliably close to the true parameter an estimator is. Okay, so we can think about, based on our simple graphs, we can think about these two criteria. These are two main criteria. I suggest. So we may summarize them like this. We are going to think about the sampling distribution, right? And we, more specifically, we are going to think about the mean of the estimator and the variance of the estimator. In terms of the mean, what we want is the mean equals to the true parameter, right? Then it does not overestimate or underestimate. It is, on average, correct. Secondly, we would like to have a smaller variance, right? Always the smaller the better in this case, right? So based on these two criteria, we will study how to find the best or a good estimator in the next video. But of course, so when I explain with figures, it's easy. But the main problem is the true parameter is unknown. In practice, you don't know where this guy is. And without knowing the true parameter, you cannot draw the sampling distribution. So that part is based on theory from the sampling distribution. So the reason why we need sampling distribution is to make this kind of graph, right? You know how to do this. That's what we are going to do in the next video. Okay, so thank you for watching. We are getting into the core part of estimation theory. So I'll look forward to the next one. See you there. Bye.